Airplanes are getting bigger and more heavy, and today they can easily take 600 tons into the air. How is that possible? What makes an airplane fly?
Okay, for an offer crossing, turn right.
Foxtrot Delta Delta 0, wind 270 degrees, 16 knots, runway 02, cleared for takeoff.
360 degrees at 7, runway 30 right.
Welcome today. This is Aviation Easy Explained for the non-aviator. My name is Frank Dreyer. Thank you for joining me today. Let's go. Let's clarify why an airplane can fly. First of all, we will look at what we cannot see, namely the air. Do we need air to fly? What is air anyway? Well, air is a mixture of atoms and molecules that is in a gaseous state. Let's remember briefly, there are three aggregate states: solid, liquid, and gaseous. For a better understanding, the states of aggregation are explained using the physical particle model. In the particle model, the smallest particles of a substance, in this case the atoms and molecules, are simply defined as small globules. Each of these small globules has an average kinetic energy, which is initially directly dependent on its temperature. The warmer the gas, the faster these globules move and bounce stronger and more frequently against each other and barriers. When and in what state of aggregation a substance will be definitely depends on the temperature. Let's take water as an example. It is frozen below 0 degrees centigrade, hence solid. From 0 to about 100 degrees it is liquid, and above 100 degrees converts to the gaseous state. But there is a second factor that influences the physical state, and that's the pressure. If the pressure drops, the gaseous state occurs earlier. At 1000 meters above sea level, water already becomes gaseous at 96.6 degrees, so it boils. At 2000 meters at 93.3 degrees, and at 5000 already at 83.3 degrees. Now we take a box, initially still open, and connect a thermometer and a pressure gauge to the box. Clearly, the air in the open box shows both the same pressure and the same temperature as the ambient air. Even if the air looks invisible, it is enriched with molecules of atoms of different substances. In dust-free air, 78% of nitrogen, almost 21% oxygen, the carbon dioxide, helium, neon, argon, krypton, and xenon. The density is used to define the amount of a gas or gas mixture. 1 cubic meter of air weighs around 1.23 kilograms at a pressure of 1013 hectopascal. This air stands still, so it is static. There is no dynamic force acting on it. This pressure is called the static or atmospheric pressure, PAT. Next, we close the box and place the heating plate underneath, which now heats the air in the box up 5 degrees. What is happening? Well, we have just seen that heat supplies energy to the globules, which in turn stimulate them to move faster. Now we can measure it as an increase in pressure. In our example, the pressure has increased by 4.35 hectopascal. Has the air density changed in the box as well? No, because we didn't add any additional gas. Now we're going back to our starting temperature of 50 degrees. But this time we are doubling the amount of gas in the box. What is happening? Now the density has doubled in the closed vessel. These additional globules now bring their own kinetic energy with them, which is why the total pressure doubles. What would happen theoretically if there were no particles in the box? Well, the result would be no measurable temperature and no pressure, because the box is evacuated. There is an absolute vacuum. If you're interested in the physical and mathematical background, Google about the scientists Boyle, Mariotte, Charles and Gay-Lussac. They have been the main explorers for this knowledge. Now we know what air is and we know the relationship between pressure, density and temperature. The next great researcher whose knowledge we need has been Sir Isaac Newton, a British explorer. In the 17th century, he had already explored the action of forces and defined them mathematically as part of his research. His first, second and third Newtonian law are the doctrine of classic mechanics to this day. For our solution, we need Newton's third law, and that means force equals a counterforce. A force from a body A to a body B always starts with an equally large but opposite force from body B to body A. Here's an example. Let's say you and I are each on a skateboard. We keep a short distance between us, and each of us takes the end of a rope in hand. What do you think will happen if I pull the rope? Do I then pull you to me on your skateboard? Well, what will happen is that the two of us will move towards each other. Your skateboard is rolling towards me and mine is rolling towards you equally. This is what Newton discovered. My power to pull you up always triggers a counterforce that is in our example pull me to you without you doing anything. Now we'll make use of this knowledge. Let's take a look at a wing profile in cross-section. We can see it is more arced up on the top than the bottom is shaped downwards. These are the slats we can be extending to the front and the flaps which can be extended to the rear and down. I will come to this a little bit later in detail. There are various different profile shapes depending on the speed range and height at which the aircraft is supposed to move. Slowly flying aircraft have a higher profile thickness than fast aircraft. The point at which the airflow hits the profile is called the leading edge. If the wing moves through an airflow, the airflow is split at the leading edge and forced to divide between the upper flow and a lower flow. The split airflows around the wing profile will meet again behind the wing at the trailing edge. Due to the profile shape of the wing, the airflow is now deflected downwards behind the wing. That's where we go back to Sir Isaac Newton. The interaction principle of his third law, force creates a counterforce, comes into effect here. The force acting to deflect the airflow downwards creates a counterforce on the opposite side of the profile, and that creates a lift force. What do the flaps do now? They lead to an even stronger deflection downwards and thus generating additional lift on the upper side, which is necessary during the takeoff and landing phase when the speed is even lower. At the same time, the extended slats enlarge the wing area and thus also generate additional lift. Great, all right. But why did I talk so much about air, density, temperature and air pressure when we have already clarified why an airplane can fly? I tell you a secret. The amount of lift force we have discovered so far is not enough. But where do we get additional lift from? You remember the static pressure PAT, which acts on us and our still ambient air? Since the aircraft moves forward due to the propulsion force, an airflow moves opposite towards the wing and as a result acts on it with a force that we can also measure as a pressure. This air pressure, which now hits the profile at the leading edge, is named PD, the dynamic pressure. And this pressure is added to the static ambient pressure PAT. I call the sum of these two pressures PT, total pressure. Before I put the puzzle pieces together with you, let's briefly summarize what we have so far. Oh, I had completely forgotten. Of course, we will write a test at the end. So you should make some notes. No, there is no such thing here. Lean back, relax. You don't have to be a scientist at all. I try my best to explain this topic as simply and clearly as possible. So please don't be alarmed if a few numbers and variables come up. You do not have to calculate anything. Now we know about the static or ambient pressure, the air pressure in the still air. Then we have the dynamic pressure, the pressure energy in a moving air mass. Both added give the total pressure PT. V is the velocity of a moving airflow in relation to a body, in this case our wing. Please don't worry about the units that I have given for the sake of completeness, like here a meter per second. They are necessary for the calculations, but I will give you the results, so you do not need to recalculate anything. We know as well the air density phi. Let's remember the particle model for a moment. The density is the amount of globules in an existing amount of gas. In our case, the amount of air that hits the leading edge. Wow, a formula. Relax, will be easy, and I promise you this short formula, namely this value V square, a great secret is hidden here. Let's quickly look at 3 examples. In a few seconds you will understand what I meant. We'll take a round number of our ambient pressure, 1000 hectopascals. The air density of 1.2 kilograms per cubic meter is also a realistic value. In our first example, we had just taken off and have reached a speed of 80 knots. To make it easy, headwind and tailwind are 0. This means that the airflow hits the leading edge with 80 knots. 80 knots, or about 148 kilometers per hour, corresponds to 41.16 meter per second. We put this value in the formula. Because the speed v is squared in the formula, v value is multiplied by itself and then by 1.2 and 0.5. The result is 10.2 hectopascals. Finally, we add this static pressure and get a total pressure of 1010.2 hectopascals as a result. In example 2, we have accelerated to 160 knots, twice the speed as in example 1. Now it's getting interesting. In the formula, as we know already, the speed v is squared, and this means that a double of the speed, the dynamic pressure quadrupled. In example 3, the speed has increased by further 80 knots. So our initial speed of 80 knots has tripled. Well, and what about the dynamic pressure? It has increased 9-fold. Keep that in mind. We need this understanding in a moment. Let's get back to our wing profile. We take a tape measure and measure the length of the leading edge to the trailing edge initially on the top. This is the blue line here. And compare the measured length with the length of the lower green line. You will notice that the blue line is longer than the green line. If the slats and flaps are extended, the difference is even greater. Let's get the puzzle together now. The distance that the airflow has to cover over the wings is longer than the distance under the wing. So the air must be accelerated above or slowed down under the profile in order to join again behind the wing. At an airflow velocity of 240 knots, we measure a total pressure of 1091.5 hectopascals at the leading edge. Due to the airflow distribution, which depends on the construction of the wing, i.e. profile depth, profile length and shape, there is about 30% acceleration of the airflow velocity on the top of the wing and a 15% deceleration on the underside. As a result, we get 310 knots on top, i.e. 158.48 meters per second. We can no longer change our total pressure of 1091.5 hectopascals, so the ratio of dynamic pressure and static pressure must be converted now. Let's use our formula again and apply the 159.48 meters per second. This results in a dynamic pressure of 152.6 hectopascals at 310 knots. If you subtract this value from our 1091.5 total pressure, we get the static pressure of 938.9 hectopascals, so a relative static under pressure of 61.1 hectopascals to the top of the wing compared to the static ambient pressure of 1000 hectopascals. Now we finish the mass on the underside. The flow velocity is reduced to approximately 204 knots, i.e. 104.95 meters per second. Replacing in our formula, we calculate at a static pressure of 1025.42 hectopascals on the underside. That means a relative static overpressure of 25.42 hectopascals compared to the static ambient pressure. Finally, to check now the average of the static pressure, we add the two pressure values just calculated from the top and the bottom. Here 938.9 plus 1025.42, the sum is 1964.32 hectopascals. Now the sum divided by 2, the result is 982.16 hectopascals. Whoa! Shouldn't the ambient pressure be 1000 hectopascals? Where are the missing 17.85 hectopascals? Let's go back to the particle model for a moment. Thermal energy can be converted into pressure energy and vice versa. That's what has happened here. After the airflow had hit the leading edge, part of the air pressure energy was converted into thermal energy and transferred to the wing, which is why the front side of the wing has heated up. Well, that's the almost 18 hectopascals that we now lack. But enough about that, I don't want to make this too complicated today. The static pressure distribution on the wing looks something like this. And the result is going to be literally a suck upwards by the static under pressure on the upper side of the wing and a push upwards on the underside of the static overpressure. The ratio between suction and pressure is around 2:1. Well, finally, we have solved the riddle and figured out why an airplane can fly. Here's something quite interesting from our findings so far. Why do airplanes fly so high when cruising? Let's remember the air density. It decreases with increasing altitude. In other words, the higher we fly, there are fewer and fewer globules in a given volume compared to our box from the particle model. In order for the aircraft to fly aerodynamically, it needs a certain pressure. However, if the air density decreases, the pressure decreases literally or linear. The solution of our here will be our benefit. At high altitudes, you have to fly faster so that enough globules flow around the wing and hence enough pressure will be built up. If you fly at an altitude of 39,000 feet, the indicated airspeed on the airspeed indicator in the aircraft still reads 240 knots, but the true airspeed is already around 445 knots. Wow, that's a lot. That was a lot. But I mean, we got through it pretty well. Clearly, many other factors also play a role, such as friction, resonance, temperature, flow behavior, and a lot more. But that's negligible to the pure understanding of why an airplane flies. I hope you enjoyed this video, and I would be grateful for your feedback. If you have any questions or other topics you are interested in, please write me in the comment box. I'm happy if you like my videos, then please don't forget to subscribe. Thank you very much. Have a nice day. See you soon.